Okay, so we're back at the interview practice. Now, let's get started with a question. So, I'm going to go onto the TBO problem solving booklet and just pick a random question from there. Actually, no, let's do a BMO question. BMO. Given that BMO is tomorrow, we might as well get some practice in. So, let's take question 3. Okay, so we have two circles S1 and S2 are tangent at P. A common tangent not through P touches S1 at A and S2 at B. Points C and D on S1 and S2 respectively are outside the triangle. Okay, so I'm going to try draw this quickly. And it doesn't say the circles are the same size, so I'll just draw two differently sized circles. It's kind of hard to make them be tangent. Okay, that's good enough. And then I'll just join these up like this. So we'll say this point is the first tangency point, and then we will also give well, I want it to be a horizontal line because I think that'll make some calculations easier, but maybe it won't be possible. Okay, let me just try and skew this circle. Okay, so here's the setup. We have let me just check if this is actually working. Yeah, and in the meantime, common tangent. Yeah, so this point would be A, and this point would be B. Points C and D. Okay, so I think it can hear this. Yeah. Okay, so yeah, back to the topic. So we have points C and D on S1 and S2 respectively. So A APB. So this is the triangle we're interested in. And points C and D are outside such that P is on the line CD. Okay, so if we had C here, then we draw a line and D would have to be here. Okay, and what we're trying to prove is that AC is perpendicular to BD. Okay, so I'll use a different color. We're trying to prove this line here is perpendicular to this line here. So what that's saying is if we extended these down, we would have a right angle there. Okay, how can we prove this? Well, this is weird, isn't it? Okay. So I'm thinking we should just try to use circle theorems in this question. Okay, what's my first thoughts? Okay, yeah, so we'll just label any angle here. Let's say we label this angle. No. Okay, let's label this angle theta. So now if we can prove that this angle is 90 minus theta, then we'll know that this angle here must be 90. Okay, so there's our goal. We need to prove that this angle here is 90 minus theta. So how can we do that? Now let's try and use some circle theorems. So, Okay, so there's a common tangent. Yep, so maybe we can use alternate segment theorem here. So alternate segment theorem is the circle theorem, I believe, which does this. So it says the angle in alternate segments are the same. I think this is it. Hopefully it is. Because if it isn't, then we will probably be completely wrong. But that seems about right. So in our case, we would have this would also be theta. And maybe I should just confirm alternate segment theorem, seeing as it is something that we should know. Okay, so let's see. Okay, yeah, so this is the alternate segment theorem. And I think this is the same here. Okay, good. So, what else do we know? So, now we know this angle. If I draw a vertical line downwards, like so, since these are tangent, a common tangent, okay, so the tangent at P, so if we draw this tangent in here, like so, then we know that angle is going to be 90, and that's also going to be 90, okay. So how can that help us? So that angle is 90. See, if I can just prove this is 90 minus theta, then we can prove this is 90 minus theta, which then lets us prove this is a right angle. But how can we get there? Right, so we're effectively equivalently trying to prove this is a right angle here. If that's a right angle, then this is 90 minus theta, and so that is also 90 minus theta. And so, okay, we're kind of making progress. So, Let's use a different color now. If we have, let's just pretend this is the radius. And so it's tangent at A, which means that's a right angle. Tangent at B, which means that is also a right angle. And we know this is a chord, right? PD is a chord, and we know we'll just write radius bisects. Hang on. Does the radius bisect chord? I think this is a circle theorem, but it doesn't seem like it's true, because what if it was like that? Wait, let me just search up what that circle theorem is. Radius bisects chord. Okay. So it's not just radius bisects chord. That's kind of silly. But okay. Yeah, okay. I think this is a pretty bad drawing, which is why it's kind of hard to visualize. But if we draw a radius to this tangent, that is 90. And we know that would also be 90 because they're tangent. And we know radius meets a tangent at 90 degrees. We know that's true. So, therefore, these two lengths are equal. And so, does this form a kite? See, I just don't know how this is helping. Wait, okay, we might be onto something. So let's use a different color. Okay, so this angle is a right angle. And therefore, we can say that this angle will be, I'm going to say just theta dash equals 90 minus theta, because we're going to be alternating between theta and theta dash quite a lot. So I'll just say this is theta dash. Okay, easy enough. And now we can use the fact that this forms a isosceles triangle to get this angle is also theta dash. Nice. Now we know this angle would be theta as well. Okay. What do we do now? So this angle here, which is not a right angle, that would be 180 minus 2 theta. There we go. Because we're just subbing up the angles in this triangle. So therefore, this angle was just going to be 2 theta since it's on a straight line. Okay. I feel like we're in a home straight here. So, okay, come on. Okay, so let's look at this quadrilateral here. Now, we have I want to say these two, this triangle and this triangle are congruent, but I need to find a way to actually prove that. How can we prove this? Okay, let's just zoom in, because Okay, so we know this is a right angle, we know this is a right angle, we know this angle here. Aha! And we know that two tangents meet at equal distances from a point. There we go. So therefore, this length and this length are the same. So therefore, okay, we know the lengths are the same. Okay, wait, hold up. So we know these two triangles, yeah, these two triangles have the same angle. They both have the 90, and they have these two lengths the same. So these two triangles are congruent. So we can say these two. Now how can we use that to help us here? Oh wait. We've literally had this angle as theta all along, which means... Oh no, never mind. I thought we might have been able to... No. And remember, we're also trying to equivalently prove this is 90. So if we show this is theta dash, would that make sense? If this was theta dash, this would also be theta dash, since it's an isosceles triangle. And do those add up to 180? So we have 90 plus 90 minus 2 theta. Yeah, okay. So this would work if we could somehow show that this is theta dash. Okay. So we have these two lengths are the same, and we have these two lengths are also the same. But what we don't have is a way to show that they're all the same. If we could show this is a right angle, then that would show it's a square, which means we could split it down the middle. Oh, wait. No, we're done. We can split this down here. Let me use green. We can split this down here. So this is clearly an isosceles triangle just because these were the same length. So therefore, we can say these two angles must be the same. And I'll just call them x for now. We'll just solve quickly for x. So you have 2 theta plus x, and that's equal to 180 degrees. So therefore, 2x equals 180 minus 2 theta, or x equals 90 minus theta, which is equal to theta dash. So I'll just replace these x's with theta dashes. There we go. And now we've got this alternate segment here. So we can say that this angle is theta dash. And therefore we'll look at this entire triangle here. And we can tell us that, we assume that this was a right angle, but now we actually can say that it is a right angle. We'll say, so now we know this angle is going to be 90 minus theta dash minus theta, 180. And luckily we know 180 minus theta dash, which is 90 minus theta. That just simplifies down to 90. So we proved that this is a right angle. So therefore, CA and BD meet at 90 degrees. And there we go, we're done. So I think I took a long way around it. I don't think we need all those steps, but it's been a while since I did any kind of geometry. So, yeah. Anyways, I wonder if I'd be able to prove it faster now that I actually know how to do it. Let me just try to do it quickly here. So let's just ignore everything here apart from the original markings in black. So call this angle theta. Then we know that from the alternate segment theorem, this angle is also theta. And then we know, since this is a right angle, we know this angle is theta dash. And then we can say this is an isosceles triangle, so we know this angle is also theta dash. And this angle is a right angle, which means this angle is theta. Okay, and then we have a theta here. We have an isosceles triangle here, which means this angle is also theta. Wait. There's a faster way. So we'll say this angle is theta, then we know this angle is also theta from alternate segment theorem. We can see this is an isosceles triangle, so we know this angle is also theta, and therefore this angle must be 180 minus 2 theta. Then this is a straight line, so we know this is 2 theta. And then we know this is also an isosceles triangle, so this angle must be theta dash, therefore this angle is also theta dash, and then we can move the theta dash over to here. And then we have this big triangle over here, so we have theta here, theta dash here, so that this is going to be 180 minus theta dash, which is 180 minus theta minus 90 minus theta, which is equal to 90 degrees. So therefore that's a right angle, and they meet at a right angle, so therefore AC is perpendicular to BD. There we go. Let's have a look at the actual solution, just to make sure we got that right. But I think that was correct. Okay. Yeah, here we go. So let AC and BD intersect at X. So yeah, we extended the line as well. And okay, common tangent, yeah. Okay, so similar diagram, of course. So they got it in 3 lines. Alright, it's alright. Let's just see what they do. So they label this angle with DCA. Yeah, they label that with gamma, and BDC as... Okay, so they actually label 2 angles instead of angle chasing like what we did. Let's see if this is a much easier strategy. By the alternate segment theorem, YPA, so this angle here, you can't see what I'm selecting, but this angle, yeah, okay. YPA, that would be equal to, that would be equal to, interesting. Okay, that would be equal to gamma. And this angle would be equal to YPB would be equal to YP is equal to gamma, and YBP equals BP equals epsilon. I think it's delta. That's delta. So gamma, delta there, and then angles in triangle BPA sum to... Okay, yep, so they sum and everything, so they know gamma plus delta is equal to 90, so therefore the sum of these 2 angles must be 90, so therefore the angle CXD or DXC is equal to 90, so therefore we prove that. Okay, yeah, cool. Okay. Solutions. Okay, interesting. Using the fact that O1P O2 is a straight line. I mean, it makes sense that it is a straight line. APB. Okay. Okay, yeah, that's fine. So a good solution there. Let's do a regular interview question now. Just to cool off, and then we'll call it a day. TBO problem solving booklet. So let's go. Okay. Okay. Alright, let's pick a random one. 67 looks kind of mean. Is tan of 1 degree irrational? How would you even think about that? Actually, okay, let's try this one. Is tan of 1 degree irrational? That's a weird question. So, how will we think about this? So, I know that tan of theta, that's equal to the opposite side over the adjacent side. And I'm thinking about a right angle triangle here. So, in a right angle triangle, if we say this is 1 degree, and then we're saying tan of 1 degree is the ratio of opposite over adjacent. Okay, so obviously we can construct a triangle which has side lengths. Let's say this had side length A, this had side length B, and yeah. So therefore, that's right. It is possible to construct a triangle, or I should say right angle triangle, a right angle triangle with theta equal 1 degree. Okay. But we need to show that the ratio A over B is a valid number. So if A and B are real non-recurring numbers, then we would have our answer, tan of 1 degree, is rational. Okay, so maybe we can do a proof by contradiction. I know that happens a lot when you're thinking about proving irrationality, but I don't see how we could do that here. But, okay, hang on. It is possible to... Okay, so let's say we start with a base of 1. So this just like 1 meter or something. And then we have our angle 1 degree there. So when we extend this line up, we're essentially hoping that this number is a rational number. Makes sense because this number, the length of this side is tan of 1 degree. So if we can show that this is a rational number, then we'd be good. And okay, let's try and make this a bit more general. So we'll say this has a length x, and then when we extend this side up, we'd have a side length of x tan of 1 degree. Okay. So we'll say if tan of 1 degree. Oh, I'm really just going in circles. I'm going to say if x over tan of 1 degree tan. Oh no, this is bad. If x over tan of 1 degree over x is rational, then, oh no, I've actually said absolutely nothing, because this just simplifies to tan of 1 degree. Okay, maybe we need another approach to this question. Yeah, I think we use a better approach here. It is possible to construct a right-angled triangle. So we know this is definitely true. It is definitely possible to construct a right-angled triangle with theta equals 1. Okay. Oh, this is a sticky one. Okay, how are we going to prove? Okay, let's think. The question is tan of 1 degree irrational? And I guess we could just add all rational. Okay. Okay, so we know a rational number can be written as a over b, where a and b are integers, not 0. B is not 0, and they have no common factor. So that's the definition of a rational number. Now, how could we show that tan of 1 can be written as a rational number, or maybe show that it can't be written as a rational number? I'm trying to think of a proof by contradiction, but I don't think it's going to work. If we say something like, assume tan of 1 is rational, so then we'd say tan of 1 degrees equals a over b. Then we might do something like a equals b tan of 1 degree. But then Okay. We also can use identity. So we know tan of 1 degree equals sine of 1 degree over cos of 1 degree. Okay. And from here, maybe we can use... No. So a rational number can be written like that. So I guess the question is, can we make a right angle triangle with angle here as 1 degree, but these side lengths are actually integers? So that's the question. It's not just real numbers, but integers. And that might be slightly more tricky. I think the answer is probably no. So the answer is probably it's irrational. But how can we prove that? Okay. Okay, let's have a look at what the answer says. That was 67. Okay. Quantity tan of 1 is not rational. Okay. We should have used... Okay. The compound angle formulas. Okay. So, we know tan of 30 degrees is in fact irrational because it is root 3 over 3, and root 3 is irrational. This is rational, so therefore tan of 30 degrees is irrational. Okay, from here, let's remember our cos angle formula. Tan A plus B, that's equal to sine A plus B. I'm probably just going to have to derive everything again, which is a little bit annoying, but it's alright. Sine B cos A over cos A cos B minus sine A sine B. And then we divide everything by cos A cos B on top and bottom. So that would make it tan A plus tan B over 1 minus tan A times tan B. So if we want to get, well, we can reduce it down to, we can figure out what tan of 15 is. From there we can figure out what tan of 7.5 is, but I don't see that helping. Okay, if we assume tan of 2 is rational, okay, tan of 2, then we get to tan of 4, and then we can get to tan of 10, and okay, so it is a proof by contradiction, but we don't actually use the A over B method here. We just keep using the addition formulas until we get to a tan of 30, which we could show is we could show that tan of 30, it would be rational if tan of 1 was rational. That's a contradiction, so therefore tan of 1 must be irrational. And then I suppose we do the same thing for cos. Okay, fine. I see how it is. Yep, that was decent training. Still have a while though, so hopefully we can improve in due course. Thanks for watching, and I'll see you guys in a future video. Bye.